Alright, today on the bench in HP 7044A XY recorder. So I'm upgrading from my 7035 from the 1960s. I'm getting one from the 1970s or 80s? 76! Calibrated in 76.
Hello and welcome back. If you follow the channel, you might have followed the previous restoration of our HP 7035 analog XY recorder. A child from the 1960s, it had a photo chopper and discrete transistor-based servo amplifiers inside, and drew on a modestly sized 7 by 10 inch surface. The HP 7044 is its descendant from the 1970s. It draws on an impressive 11 by 17 inch or A3 paper format. And this time around, we expect integrated operational amplifiers inside.
Those are hard to get because they are either outrageously expensive or people don't know how to ship them. This one falls into don't know how to ship them category. It's a miracle it survived. Or maybe it didn't. Turn it on. Woo, 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 woo. Okay, there's life. There's life in the x-axis. And he showed some x-axis life and not y-axis, so I didn't expect the y-axis to work. Except it actually does. Well, kind of. But wait, it shouldn't. It was in standby. So why is it not standing by? It's missing its rear connector here. I don't think there's a delete option, or maybe they hardwired it inside. We'll see. Unfortunately, the user manual is not available, so I sprung up from buying one and being extorted on eBay, but then I'll scan it, make it available for everybody, and nobody else will be extorted anymore. I see another thing that's not right. This has delaminated. That's for the electrostatic holding plate. And this is not broken. So in general, man, I got lucky because when I got the case, I thought there would be nothing left of it. Alright. Woohoo! Okay, this is fine. Why doesn't it have the connector? That's so weird. I see no evidence of anything being cut. Maybe it is an option to delete that. Aha! Found it in the catalog. 1973. New in 1973, 7044, 7045. 744 is the regular model, the 745 is the race model, it goes much faster. Okay, the mystery of the missing rear connector is explained. It is actually optional. I have the 001, I have the time-based. Wasn't cheap, 1350. I think the front is gonna come off if I take these screws out. Okay, yeah, that works. See if we've made progress. Ooh. I'm not sure that we've made progress. We have some interesting add-on. I don't think that's original. Yeah, the pot is definitely in there. You can see the gold portion of it. But it looks fairly clean, so I'm going to give it a clean, but I don't think that will solve my problems. Okay, we keep going. Yes, it can be done, and if I remember well, in the 35 it had cables behind. It does. Ah, there you go. It's the rail here that I want to clean, and then I want to put some dielectric grease on it. So step 1, isopropanol. Yeah, needed some help. Step 2, deoxide gold. That's what actually is going to do the real work. Step 3, dielectric grease. On. It's not a contact, it's something the power supply I would suspect first. We can do the same cleaning over here. Not clean indeed. Okay, same issue. Over here, the platen. Looks like it's a piece of PCB with electrodes behind and a foil on top. You just need very thin glue, so cyanoacrylate super glue I think will do the trick here.
Meanwhile,
so I probed around the voltages to see if there's something obvious, and I didn't see anything wrong with the filter capacitors, nice voltage on them. But then I looked at the point where it says plus 15 volts and it's plus 9, and on the other board I know it's plus 15, so we already have a power supply issue somewhere. So I think rather than reverse engineer the whole thing, I'm going to wait for the expensive schematics to appear from eBay. Alright, I got the manual, it's all scanned, so everybody now has access to it. And I already found something that I shouldn't have done. It says, caution, do not use slide away lubricant on either X or the Y slide wires, which I already did, dang it, so maybe I'll remove it. And during that time I played a little bit more with it. It goes to 0.5 millivolt per inch, which is ridiculously sensitive. So it's fine if I do this, because I've shorted it. But if you don't short it, it just picks up stuff. There you go. So X seems to be working, and there's a good way to try it is to use a time base. So it works fine, and then at the end it has a problem. It's getting better. And I can feel it, so if I stand by right here, it becomes stuff. So it's mechanical. However, we do not have Y working. It worked for a second, but then it quit. So now that we have the manual, we will probably be able to figure out what's wrong. First things first, I need to check my cable tension, and I just checked it and it's too low. It says if you deflect half an inch like this, it should be at 20 ounces. I am at 12 ounces. There's a screw right here to adjust the tension. I'm doing it. There you go, I'm at 20. Okay, so that should be good. Much better. Okay, so that fixed it. So let's do the juicy stuff now on the back. This is Y. And this is the one where we were measuring suspect voltages. They're totally independent. They're not grounded together. So they have their own floating power supply. This is my ground. I checked that I have plus or minus 24 at the cap. And then I'm looking at the plus 15. It's actually written on it. And if I turn it on, it's plus 9. So I have the correct voltage over here, and then I measure 9 volts instead of 15. So if I understand this power supply correctly, at equilibrium I have 15 volts across the zener. I should have about 0.6 volts over here, which will turn on the transistor just enough so that I have 15.6 volts over here. I'm going to put myself over here. I expect less 9.6 because I don't have 15 volts at the output. Yeah, 0.395. So I am right here now. That transistor should be off, so it should be close to 24 volts. It's not. It's at 10.7, which means, yeah, it's no wonder on the other side of the transistor I'll get that minus 0.6 volts, so I'll be close to 9.9 volts. It's either this cap is leaky and bringing this voltage down, or this transistor is bad. So I think the simplest experiment is to lift Q12, and if that one is the shorting problem, then I'll know right away. Okay, well, that was easy. Let's see if that regains me some 15 volts. That's 15, will be this one. No, I'm still at 10 volts. Okay. So not the cap. Right, I extracted the transistor. Alright, here's our suspect transistor. And oh, not a transistor anymore. Okay, zero transistor action. Q12, which is in HP speak 1854-0215. Thankfully, they give us the equivalent. It's the garden variety NPN transistors 2N3904. So we have the actual transistors. Okay, let's see if we got 15 volts back. Yeah, a little bit more. We got 16 volts. Huh. And that seems a little bit too rich. What do I have on the other side? 15.44. And then if I go to the minus 15. Oh, that's minus 16.51. Okay. So I guess it's not very precise, depends on the zener. Alright. The other side ain't any better. So let's see if we have recovered our amplifier. On. Nope. Do we have X? We still don't have Y. So I don't get no action. Actually, I do get some action. It goes all the way down. It's just this portion. Nothing else bothers it.
Let's briefly interrupt this restoration so we can explain how the servo loop works, or should work, because at this moment it really doesn't. Here is the beautiful schematic of the Y-axis amplifier, now available to everyone, link in the doodly-doo. It has three main parts: the power supply, the input signal amplifier, and the motor servo loop proper. We hopefully just repaired the power supply, so we'll assume it's good for now and not worry about it. We have not fully tested the input amplifier, but we have good reason to think it works. It gave us solid noise response when we tested it without grounding it. Then it quieted down when we grounded it or turned the sensitivity down. It looks like it's amplifying stuff alright, so we assume it's okay for now. That leaves us with a probable culprit, which is the servo loop. That's the bit that's supposed to move the Y-axis motor to the right position. Let's look at it in more detail. First, there is the Y motor, of course. We just saw it move all the way down when we took the machine out of standby, so that seems to work. The motor current is controlled by an amplifier stage consisting of 4 transistors. It's just there to fortify the output of the op amp that precedes it, so it can drive the motor. The op-amp itself is the key component of the servo loop and is wired as a summing amp. It's our little analog computer at the heart of this device. To see what it's adding, we just have to look at what comes into the summing point at the minus input of the op-amp. The first input is our amplified Y signal. That's the signal we eventually want to use to drive the motor, but in the following test we'll turn it down to 0 so we can ignore it. Instead, we'll use the 0 potentiometer as our input signal. It's simply added to our input signal anyhow, so it makes for a nice test input. We should be able to move the pen to any Y position using this knob, but clearly we can't. The pen is stubbornly stuck at the bottom no matter how I twist the 0 knob. Now comes the Y position input. It's a voltage that represents the position of the pen and is produced by the big resistive slide that we just cleaned, which is just a giant linear potentiometer. Note that the signal goes first through another op-amp wired as a unity gain buffer, so the impedance of the slide wire does not affect the sum calculation. The main point, of course, is that the motor moves the slide, and therefore the circuit is a big loop, part of which is electronic, part of which is mechanical. It's the so-called servo loop. There is yet another input to the summing point that we want to mention for completeness. It's the negative electrical feedback taken from the output voltage of the power stage. This is to limit the gain of the loop so the motor doesn't overreact and the whole thing becomes unstable. You can see how it is carefully filtered to make the loop well behaved. Now, the masterful trick is to choose the mechanical and electrical polarities so that the Y position signal is subtracting from the Y and 0 inputs. As we will see in a second, this will result in the motor moving so that the summing point always goes back to 0 volts. Let's suppose the summing node is at say 0 volt, so there is no voltage applied to the motor, nothing is moving. Then let's move the 0 knob up a bit. A positive voltage temporarily appears at the summing node, which is then amplified and applied to the motor, which starts to move the slide. The Y position voltage now grows more and more negative until it cancels out the increased 0 knob voltage, bringing back the summing node to 0 volt. The amplifier output goes back to 0 and the motor stops in its new position. It is said to be servoed to the input voltage. But clearly right now it doesn't do that. Now, loopy circuits are notoriously difficult to debug. The fault could start at any point in the loop, but then it propagates around. So often the signals are wrong all around and it's hard to know what's a cause and what's an effect. Let's see if we can figure this one out.
So right now I am on C8, which is over here, it's on the side over there. And that will tell me what the motor does. So on, and this is on standby. Let me move this thing a little bit higher, you'll hear it if it goes down. Yeah, it went down because it has 10 volts. So this did something. So now I've moved myself in between those two resistors, so it should be at 0 when I am on standby. And it should hopefully be close to 0 when I release it, and I bet you it's not going to be 0 volts. I'm going to move this thing a little bit up. Whoop, 12 volts. So it's 12 volts here, and then it's amplified and I get my voltage over there. So this seems to work. Now, why is it 12 volts? Oh, I should be able to vary here. This 0 control over here. Then that should vary. Okay, let's do that. So right now I put myself right over here on the pot side of R26. And it's going from minus 6 volts or plus 6 volts to minus 6 volts. So it's exactly what it should do. I'm going to put it at 0 and And then on the other side, I would want to have 0 volt or something similar. If I do this, get myself here, I have 0.726. But then it's also influenced by the position of the slide. I just put the slide over here in the middle. And it's 0.26, and I should be able to bring that to 0 right here. So that appears to work. Now if I do this, since it's at about 0, it shouldn't move. Oh, it didn't. Oh, it repaired itself. Now the loop maintains it at 0, that's correct. What did I do? It just got fearful that I measured it, and it worked. Okay, I don't like it too much when things repair themselves, and I don't know why. Because they can also unrepair themselves without me knowing. This is 1 volt per inch. Oh! Look at that! It unrepaired itself. Told you. What? It's when it goes below. Huh! It's fine. Now when I get down there, boom! Something goes to the rail. It ought to be one of the amplifiers that rails.
Early op-amps were infamous for being susceptible to lockup when the output was brought close to the voltage supply rails. It looks like this is exactly what's happening here. Maybe my op-amp is faulty and is succumbing to lockup.
So my suspicion is that this guy locks up. To see it, actually, it's fairly easy. I connect myself to R21 and I move the slide wire by hand while it's on standby. And if this one just goes fine, then locks up, I know that's the problem. I should go up and down when I move the slider up and down. It does. Oop! See how it locked up? It went 0, minus 0.3, jumps to minus 12 volts. Is that fellow? That's bad. And I don't have an LM201, but I have a metal can 741. Is a pin-to-pin compatible replacement to the 201, but better. So fortunately I have this little sockets. Yep. Okay, new op-amp, and while I was at it, I replaced the Zener, which measured okay, except it was 16 volt instead of 15 volts. So now if we turn it on, 15.24 volts, a lot better than 16.9. All right, counting on success. Works. No, still the same problem. Huh, did I replace the wrong op-amp? Yes, I did. I replaced U4, not U3. Okay, new op-amp, and I replaced that guy where it was. That's the original one. So that was U3, and I replaced U4. See if that works better. U4 back to the original, U3 replaced. Nope, still not doing it. I'll have to come up with an alternate theory here. Not the op-amp.
Soon after.
Okay, I think I know what's happening. I'm measuring the resistance from the wiper of the slide. Slideware works until we get to here, and boom, there I lose the contact, and then the amplifier goes bonkers because it has no high impedance, nothing input in it, not tied to ground anymore. I can't see very much. The slideware is buried inside here, and it's super hard to see what's happening. There's one wiper that goes over the black thing, which is the resistor, and another one that goes down here. Let me look at that closely. Okay, I think I got it. Is the contact that rides on the middle black track that had been knocked off. It's a little V on the end of the spring, and it was riding on the side instead of riding on the top. And after delicate tweaking, I was able to put it back in the middle of the track, and now I go from 0 volt to 6.2 volts, so I expect it will work. Yeah, victory. It works. Okay, so I can probably put back the original amplifier. There was no problem with it, and fortunately it's on a socket, so that's going to be easy to do. And I calibrate it, and that should be it. Alright, so curiously, this machine was missing both indicators, so I stuck a little reference line here for the 0. And same thing here. There is actually a little slide where you can put something that's supposed to be an indicator, and that was missing, so I think that's what the straw was for. But I made a little bracket imitating my 7035. You're supposed to calibrate it on 0.1. That's what we are, on 0.1. Here I have my trusty voltage source, not the greatest in the world, but close enough, 1.004. So let's see, in X, put it at 0. That's 1 volt, and it's pretty close, this little guy, and I'm going to turn it. And yeah, there we go. Let's see if I can do 1.5. Woohoo! Right on the money over here. You have to do of course, the offset adjustment before the range. So now I am good. 0 here is the same as 0 here. And note that the plotter came with a few pens. They have a special shape, so they go in here and you twist them in. And they say use before 12/25/1983, and I think that's what happened. So we did it exactly right. We used them before 12/25/1983. Of course, they are mostly dry, but the tip is good, so I think if I find a way to put back ink in there, I might be able to revive them. I have some ink, so the ink comes from this Staedtler Lumicolor permanent thingy, meant for pencil that recharge through, you insert them in there, and there's a little wick, so you have to drill them out to get the ink out of them, which I have done. So here's my red ink. So if you look at the pen, it separates right here in between the tip and that. So I'm going to pry it open. Ah! Worked. Ta-da! And then we'll do, so this time I'll do 15 milliliter. Some down. Bottom first. Yeah, so 15 is the ticket.
I soon found that re-inking the felt reservoir wasn't enough. The tip was too dry to start quicking the ink. To reprime the tip, I had to submerge it in ink for a few days.
So this one works quite well, and this one works fine too. So the difficulty is not to refill the reservoir, is to get the tip to wick. So let me show you an alternate method for this pen actually, which was already broken apart. The tip would just stay dry all the time, and I tried to soak it in anything I could, and that would never work. So alternate method that what might work better. This Sharpie pen will work fine. So first we have to take the Sharpie pen apart. Okay, we pull the tip, and this one will be a little taller. So I file the top, and that should fall right in, but before I do that, let me put the ink reservoir. Okay. Ooh, full of ink. There you go. I got it. And I think this one will fit. It will. We're going to cut it right about here. Bloop. Hello. Put the tip in. And this one is sturdier because it's metal. There we go. So here it is. And then that should go right in, yeah, because I have the hole right in the right place. Glue all around. Up. So here we go, transplanted.
Most excellent. I felt pretty good after this repair and set the recorder aside. I came back to it after a few months when it was time to film a demo plot for this video, and then this happened.
Well, we're backtracking big time here. I was going to make a final demonstration plot. I tried the thing on and the arm wouldn't move correctly, and I felt it was all loose. We had heard a big bang in the lab and we could never find what did the bang. And what has happened is that the plastic piece that supports the arm and also as the tensioning, it just shattered. Pretty catastrophic. So of course that was separated. That's how you tension it, right? So those two put a lot of tension on the part and it just shattered. There you go. And I have a suspicion that the part was molded around the sleeve bearings. If I recast the part and if I try to shove those in, they'll just not be aligned precisely enough. So we could cut this part and remake a new top. That's another possibility that I could make in aluminum.
A little longer than a few minutes later.
Okay, so I went for the easiest solution first. I JB welded the whole thing, and I made a little mold with Captain tape so I can fill it up. JB weld has the advantage that it stays a little soft. It won't break away, but still, it's a quick fix here. Okay, Captain tape trick worked, I think. And now we have the interesting rethreading problem. And then comes back, oops, in and goes in there. And that's the special screw. Will I reach? Yes, I will. And then it grabs the slider, so I didn't plug the hole, it slides free, so that's good. And that's where I'm not so confident. How much tension can I put on this without it shattering again? This time I'll use the digital gauge, also it's a little bit more cumbersome. And it's 13, yeah, I tightened it very gingerly. 19, 20. Okay, we'll call it good at 20, which is the lower limit. Okay, we don't want to leave that in there. Okay. That one works. That one does not work. How come? Did I bend the contact when I unmounted the thing? Oh no, they go the other way around. Ooh, I mounted that incorrectly. And contacts protrude over here, and I think they have to be on the other way around. Oh yeah, they're springy. All right, yes, because by default they spring back, and now I think I got it. Yeah, so their default position will be to unspring. Okay, I wish they said that in the manual. And now the scale retentioning exercise. Actually, the better way to do it is in this direction. It should be symmetric, right? And here I can do it with the little hook. 20 on that one. 20 on that one. Okay, they agree, and we're at 20 on the bottom of the spec. So we're just perfect. Okay, we'll call it good. So I've made a little setup that uses the table as I used to do when I was a young engineer. Actually, I had one of those tables. And I used to make laser diodes, and that's how I used to measure them. So there is a modern laser diode, this one is visible so you can see something, driven by a current generator, and has also a little temperature controller. And here I have an HP photodiode hooked up to a 410C, which we just repaired. Actually, this can measure microamps, so it will do fine. And then we are going to do what's called an Li curve of the laser, which is the light versus current curve. That was a big day, you know, when I started with a wafer of gallium arsenide, and I toiled in the clean room for a week or two, and at the end I made my little laser, and then that was the moment of truth to see if they were lasing good or not. So this one is a fairly powerful green. Turn it on for you just for a second. I defocused it because it's so powerful. So right now it's an LED, and bang, now it's a laser. So let's do our Li curve. Record. Because I'm an idiot and I use a 410C, it's very sensitive, but it's very, very slow. So I just have to go super slow so the 410 has time to settle and catch up by using the power of the photo chopper. There you go, turned into a laser. And now it's putting some power out. Yeah, so if I go too fast, 410C is not fast enough. It's a fairly powerful laser. I think it goes to 30 milliwatts of green light, which is actually pretty good. Here we go. Here you got the threshold current, and then here it's an LED, spontaneous emission of light. So once in a blue moon, an electron decides to turn into light. And now it's a laser and it's stimulated emission, and every freaking electron that makes it into the junction turns into light. And you can see how much more efficient that is. And if there were no defects and no non-radiative recombination, this is 100% quantum efficiency. So from the slope of that curve, you could figure out how close you were from the quantum limit. Okay, for round 2, I actually went to the electronic flea market in Silicon Valley. It's full of good stuff, and I found a thermal pile with a proper 1980s parameter, so that has a proper op amp in it. So let's try it. Take 2. Laser Li curve. There you go, now we don't have to wait. It's going to be a nice straight curve. Here we go. And that's a proper Li curve, and then you can see a little bit better the thermal effect where it's starting to bend a little bit. It's because it's heating up internally at that level of power. But here you go, quick analog measurements, unbeatable.